Welcome to this tutorial on accelerating PyTorch Transformers with Nested Tensors and torch.compile. This notebook is based on the official PyTorch tutorial by Mikola Gawerki, with additional plots, detailed explanations, and my own insights. Today we'll explore how to build high-performance transformers using PyTorch's modern optimization toolkit. Let me share what we're going to learn today. We'll replace padding with memory-efficient nested tensors, achieve 5 to 10x speedups using optimized kernels, implement transformers with minimal code complexity, and apply custom attention patterns via flex attention. Before we start, you'll need PyTorch version 2.6.0 or higher with nested tensor and torch compile support. A CUDA GPU is recommended for the best benchmark results, and you should have a basic understanding of attention mechanisms. Let's start by setting up our environment. We're enabling Matplotlib inline for visualization in Jupyter. First, let's import our core PyTorch modules. We need torch for tensor operations, torch.nn for neural network layers, torch.nn.functional for functional operations like scale.product attention, numpy for numerical operations, math for mathematical constants, and timeit for benchmarking performance. Now importing Matplotlib for creating our performance visualizations. Let's check our PyTorch environment to see what version we're running and whether we have GPU acceleration available. Great, we can see we're running PyTorch version 2.6.0 with CUDA support enabled on an NVIDIA RTX A6000 GPU. This will give us excellent performance for our benchmarks. Now let's dive into nested tensors and understand how they eliminate padding overhead. Traditional transformers require uniform sequence lengths per batch, which causes significant inefficiencies that we're going to solve. The padding problem is real in conventional implementations. We have wasted computation from processing meaningless padding tokens, memory overhead from storing zeros that don't contribute, and complex masking logic required throughout the model. Let me demonstrate this with a simple example. Here I'm creating a simple example with 4 sequences of different lengths. We'll simulate tokenization using character length for simplicity to see how much padding we actually need. As you can see, our sequence lengths vary from 2 to 18 tokens. The maximum length is 18, which means we need a total of 34 padding tokens across our batch. That's a significant amount of wasted computation. Let me visualize this padding waste with a simple bar chart showing actual content versus padding for each sequence. This visualization clearly shows the padding waste problem. The red sections represent padding, which accounts for 47% of our total tensor size. That's nearly half of our memory and computation being wasted on meaningless values. The solution to this problem is nested tensors with the torch.jagged layout. These maintain variable lengths natively with zero padding, enable faster computation by processing only meaningful data, and provide cleaner code with no mask management needed. Let me create an example nested tensor to demonstrate how this works. I'll create 4 sequences with different lengths, just like our text examples, each with 128 dimensional embeddings. Then we'll combine them into a nested tensor using the jagged layout. Perfect. Notice the shape shows J1 for the jagged dimension. This means our batch has 4 sequences, each with its own length represented by J1, and all have 128 dimensional embeddings. The nested tensor automatically handles the variable lengths without any padding. Let me visualize the difference between nested tensors and traditional padded tensors to make this crystal clear. This comparison shows the key difference. The nested tensor on the left only stores actual data with no wasted space. The padded tensor on the right has gray areas representing padding that wastes memory and computation. Now let's analyze the memory impact of using nested tensors versus padding. I'll calculate the actual memory usage for both approaches to quantify the savings. Excellent! The nested tensor uses only 4,864 elements, while the padded tensor requires 9,216 elements. That's a memory saving of 4,352 elements, or 47.2%. In production systems with large batches, these savings become even more significant. Now let's set up some utilities we'll need for our benchmarking. First, I'll create a function to generate realistic sentence lengths using the ZIP distribution, which models word frequency in natural language, where a few words are very common and most are rare. Let me explain our batch generation utility next. This function generates a batch of nested tensors with variable sequence lengths. It creates semi-realistic data for our query, key, and value tensors that we'll use in attention mechanisms. Now for our benchmarking utility. This benchmark function will help us measure both execution time and memory usage for our performance comparisons. It ensures proper synchronization for accurate GPU timing. Let's review the core building blocks we'll be using for optimization. We have 4 main building blocks for our optimized implementation. First, nested tensors using torch.nested represent variable length sequences without padding and eliminate padding masks while improving memory efficiency. Second, scale.product attention, or SDPA, implements the attention formula with automatic backend selection, including flash attention, memory efficient, and math backends for CPU and CUDA. Third, torch.compile provides JIT compilation with different modes like default for balanced optimization, reduce overhead to minimize framework overhead, and max auto-tune for maximum performance with longer compile time. Fourth, flex attention enables custom attention patterns like alibi, relative position, and sparse attention, while maintaining kernel fusion benefits through a simple API. Now let's build our optimized multi-head attention implementation. The key optimizations in our implementation include packed projections using a single linear layer when Q, K, and V dimensions match, native nested support to process variable lengths without padding, efficient reshaping to minimize memory copies for multi-head operations, and optimized SDPA with automatic kernel selection for the hardware. Here's our optimized multi-head attention class. This implementation has several key improvements over the standard torch.nn.multihead attention. It provides native nested tensor support, eliminates the need for padding masks, and achieves better memory efficiency. Let me walk through the key parts. In the initialization, we use packed projections when Q, K, and V have the same dimensions for efficiency. In the forward pass, we first do input projection, then reshape for multi-heads, apply scale.product attention, and finally do output projection. Now let's move on to performance benchmarking to see the actual improvements. We'll test with realistic parameters to simulate production workloads. I'm setting up our model configuration with a batch size of 512, embedding dimensions of 512, 8 attention heads, and we'll use GPU if available. Let me display our configuration settings. Perfect. We're configured with a batch size of 512, embedding dimension of 512, 8 attention heads, and we're running on CUDA for optimal performance. Now let's generate our test data. I'm generating nested tensor data with realistic variable sequence lengths using our ZIP distribution function. Let's look at the statistics of our generated data. Interesting statistics here. We have 11,312 total tokens in our nested representation, with sequences ranging from 1 to 151 tokens and a mean length of 22.1 tokens. This represents a realistic distribution of sequence lengths you might see in practice. Now I'll convert our nested tensors to padded tensors for comparison with the vanilla implementation. The padded tensor shape is 512 by 151 by 512, requiring nearly 40 million elements. Compare that to our nested tensors' 11,312 actual tokens, and you can see the massive overhead from padding. Let's visualize the sequence length distribution and resulting memory waste from padding. First, I'll create a histogram showing the distribution of sequence lengths in our batch. This histogram shows most sequences are relatively short, around 10 to 30 tokens, with a long tail extending to 151 tokens. This is typical of real-world data. Now let me create a pie chart showing the memory usage breakdown between actual data and padding. Remarkably, 71% of our memory is wasted on padding. Only 29% contains actual data. This clearly demonstrates why nested tensors are so valuable for variable length sequences. Now let's set up our models for comparison. First, I'll create our optimized multi-head attention layer with the same configuration. Next, I'll create the standard torch multi-head attention for comparison. Now I need to copy the weights from the vanilla model to our optimized model to ensure a fair comparison. Both models will have identical weights. Models initialized with identical weights. This ensures any performance differences come from the architecture, not from different weight values. Now let's use torch.compile for JIT compilation with the default mode for balanced optimization. I'm compiling both models with torch.compile to enable automatic optimizations. Models compiled with torch.compile. This will enable operator fusion and other optimizations for better performance. Let me run a warm-up pass for the nested tensor model to trigger compilation. Nested tensor model warmed up successfully. The first run triggers the JIT compilation, and subsequent runs will be much faster. Now we need to create attention masks for the vanilla implementation. First, I'll create the padding mask that tells the model which positions contain padding. Next, I'll create the causal attention mask for autoregressive modeling. Let me check the shapes of our masks. We've created our masks successfully. The key padding mask is 512 by 151, and the attention mask is 4096 by 151 by 151, which accounts for all heads across the batch. Now let's warm up the vanilla model as well. Vanilla model warmed up. Both models are now compiled and ready for benchmarking. Now for the exciting part, let's benchmark the forward pass performance. Running forward pass benchmarks. Running forward pass benchmarks now. First, I'll benchmark our nested tensor approach. Now benchmarking the vanilla padded approach. Let me verify the outputs are identical to ensure correctness. Excellent, the maximum difference between outputs is essentially 0. Confirming our optimized implementation produces identical results. Let me create a visualization of the performance improvements. Impressive results. We're seeing a 5x speedup in execution time and saving 0.3 GB of memory. The nested tensor approach is dramatically more efficient for variable length sequences. Now let's benchmark the backward pass performance, which is crucial for training. First, I need to clean up the padded results for a fair comparison, then run the backward pass benchmarks. Running backward pass benchmarks now. Benchmarking both backward passes. Let me visualize the backward pass performance improvements. Absolutely remarkable. The backward pass shows an 85x speedup and saves 0.4 GB of memory. This massive improvement in gradient computation will significantly accelerate training. Finally, let's verify that the gradients are correct by comparing them between implementations. The gradient differences are minimal, within numerical precision limits. This confirms our optimized implementation computes gradients correctly while being dramatically faster. Let's summarize our results. In conclusion, we've achieved impressive performance gains. The forward pass is 5 to 10 times faster for inference. The backward pass is 10 to 100 times faster for training. Memory usage is reduced by 50 to 80%, allowing larger batches, and the code is simpler with no padding masks required. The key takeaways are that nested tensors eliminate padding overhead completely. Torch.compile provides automatic optimization. SDPA selects optimal kernels automatically, and these are production-ready performance improvements. This approach is ideal for variable length sequence processing, memory-constrained deployments, and production systems requiring maximum performance. Consider alternatives only for fixed length sequences or legacy PyTorch versions before 2.6.0. For more information, check out the PyTorch documentation on nested tensors, torch compile, SDPA, and flex attention. Thank you for following along with this tutorial on accelerating transformers with nested tensors and torch compile.